Hello, I'm Barry Sullivan, Program Director for the Electrical and Computer Engineering Department Heads Association. It is my pleasure to introduce this ECE Spotlight from Quanser. And speaking will be Lior Grebler, who's the Academic Solutions Advisor from Quanser. Lior?
Thank you very much. Good afternoon, everyone. My name is Lior Grebler, and I'm with Quanser. For the next couple minutes, I'm going to be discussing with you the coming renaissance in engineering education. And we're going to be seeing a big shift in how engineering is going to be taught, and I'll share with you some examples of how different universities are preparing for this. One of the joys of working for Quanser is I get this opportunity to visit schools across North America, so across U.S. and Canada. And over the past few years, I've had a chance to meet with many of your colleagues, as well as meet with some of the people in this room. But even though I get this really amazing opportunity to see all these research labs and instruction labs, I'm still a little bit jealous of you guys, because it's a very exciting time to be involved in engineering education. We're on the cusp of some dramatic changes in human history, a period of time when the rate of change is going to start to increase exponentially. And it's you guys who are the ones who are going to enable the people who are going to make this change happen. And Ray Kurzweil, who's a futurist, refers to this era as a singularity. And its approach is getting faster and faster. And if we look at Moore's Law, and look back over the past 100 years, you can see that it's continued despite perceived limits to it. So it's continued through political turmoil, it's continued through war, through different natural disasters, and even when we thought that there was going to be a limit to how fast punch cards could compute or how fast vacuum tubes could compute and even transistors, we've been able to push through it. And if we look forward, by the end of this decade, we're going to have computers that are as powerful as the human brain. And looking forward to the next 20 years, we're going to have a computer that's as powerful as all the minds of all the humans that have ever existed on the history of the planet combined. So that's pretty incredible. But we're starting to see a couple of glimpses of this right now. And just last month, IBM's Watson crushed two of the best Jeopardy champions in a game that's considered to be, the pinnacle human strength. But also a couple weeks ago, we had an announcement from President Obama about a $126 million grant in exascale computing. So big changes are happening. And one of the things we need to ask ourselves, how is this going to affect graduates that are coming out of our engineering programs? What type of challenges are they going to face? And, beyond the problem of total world domination by computers, what type of problems are they going to need to solve? And at least in the next 5 to 10 years, for engineers who are coming out of programs, we at Quanser feel that there are going to be 4 key areas of opportunities. And one of them, of course, is in nanotechnology, especially in mobile devices. We're going to see big advances in robotics, especially medical robotics and in-home robotics, like this Keep-On robot for teaching autistic kids. We're going to see advances in unmanned vehicles. We're starting to see this with the Google car. And another area is going to be in haptics, which is the transmission of the feeling of touch. So looking ahead, one of the things that we need to ask ourselves is, how do we prepare our engineers for this new era? And before we can do that, we need to take a look back at how engineering has traditionally been taught. And when engineering first became a discipline distinct from the natural sciences, an engineer was a do-it-all. Engineer was the go-to guy, and very typically guys, for solving problems. We gave them a common toolkit of physics, of math, of science, and they used that. They applied that knowledge to solve problems. And as industry started to become more and more varied, they asked for engineers who had more specialized knowledge. People who could build infrastructure, people who could, design electromagnetic systems, people who could design roadways, bridges, and then we needed engineers who could design the vehicles that would ride on them, and eventually computers that would power all of these systems. And as industry again became more and more varied and asked for more specialization, this specialization ended up blurring the lines between different engineering areas, different disciplines. So now we're left with all this complexity, and we're left with these systems that require a new type of engineer. New engineers will need to work across multiple disciplines, across different cultures, different geographies, and of course they're they're going to require different languages as well. And it's going to be extremely rare that there's going to be an engineer who's going to be able to understand all the components of a single system. And I'll give you a simple example of this. This is a mouse. There's no one person on the planet that has the knowledge to design and build all the components of this mouse, when you think about it. It requires a knowledge of, photonics. You need to know human factors. You need to know more and more about haptics, chip design, the wireless communication, even wireless power now. And putting this all together, there's no one person who has all that knowledge. We have to work together with different disciplines. And this is a simple system compared to many of the systems that are available now. So while a systems approach has been around for a while, one approach that is being taken by the University of Texas El Paso is a new stream of engineering altogether called leadership engineering. And the idea is to create a new general engineering degree with engineering students specializing down the line, kind of similar to the medical school model. So engineers will be prepared to face a wide variety of problems, and when industry needs it, they'll be able to specialize. But going back to the mouse example for a moment, one of the skills that engineers are going to need more and more to solve these complex problems is going to be creativity. And this is a problem, because as we tend to go through our education and eventually into our careers, our creativity tends to be drained out of us. And an example of this can be seen in the paperclip test, and is also known as the Guilford Alternatives Use Test. It was developed in the late 60s, and it basically goes like this. You're given an object, and you have a certain period of time to come up with the most amount of uses for that object. And if you come up with a lot of uses, you're considered to be a creative genius. Fewer uses, not so much. And a longitudinal study that was conducted in the book Breakpoint and Beyond found that when they looked at the group of adults, 2% of them scored at the genius level. But the same group, when they were only 8 to 10-year-olds, 32% of them scored at the genius level. And the exact same group, when they were only 3 to 5-year-olds, 98% of them scored at the genius level. So somewhere along the route, these sweet kids had the creative juices sucked out of them. And many people are blaming their education and pointing the finger at their education as the culprit. Now, we aren't completely innocent of this within engineering. The way engineering has traditionally been taught was without really engaging the senses. You were given textbooks, you were given lectures, and then you were supposed to magically absorb the material, and if you didn't, you were a bad student, not worthy of an education. And the same stifling occurred in the traditional structure of an engineering program. In the freshman and sophomore years, we gave students the basics, multivariable calculus, physics, infinite series. Then later on in their studies, we sprinkled in some theory, which looked a little bit more like math. And then towards the end of their studies, we added some application. So we added a little bit of a lab course, some hands-on components towards the end of their education, and a capstone project at the end to put it all together. Now, although this layout made a lot of sense logically, where you start with the foundation, start with the basics, and build upon it, it actually alienated a lot of students earlier on in their studies. So students really didn't see the connection between what they were learning, especially early on, and what they wanted to do as engineers. So, this tended to be a little bit of a problem. And the problem is even bigger when it comes to controls, which is where Quanser specializes, because when someone's encountering controls for the first time, what's a controller? How do you visualize a controller? What are some examples? Although a lot of examples exist, when you're just learning it through textbook or through a lecture, it's about the teaching equivalent of turkey jerky. And not to insult anyone who likes turkey jerky, but it's pretty dry and bland. So this is where Quanser comes in, not turkey jerky, but in controls education. And Quanser was founded just over 20 years ago by Dr. Jacob Abkarian, who is a professor at the University of British Columbia. And he was teaching controls, and he found that those students were able to get the other topics fairly easily within engineering. When it came to controls, they were flunking. And he was really scratching his head for ideas, and in the end he decided to come up with this series of experiments to help teach controls. And the result was that students ended up doing quite a bit better. So we started off with this DC motor to be able to teach them controls, and then there were different add-ons that could be put on top of it to help teach the topic. And what he found was that the problem actually wasn't only in his course, but was very common to schools across the world. And the idea spread, and now there are about 2,500 universities worldwide that are using some type of Quanser product, including most of the universities that are represented in this room now. So one of the mottos that we have at Quanser is captivate, motivate, and graduate. And the idea behind this is that you want to excite students with some type of hands-on learning, and when they can have something to play with, it really excites them, it captivates them. They get very interested. And then when you have students who can see that if they master a topic that there's some type of tangible result, it motivates them to continue working on their problems and actually master the topic. So that's the motivation part. And then the last part is if you have motivated students, very excited about coming to labs, very excited to doing well, they end up graduating. And when they do graduate, they become engineers who are open to tinkering and playing and developing the creativity that they're going to need for this new era. So a few examples of this. Someone encountering this for the first time might be a little bit lost, but if they have some type of equipment to play with, some way of applying the theory as they're learning it, then they can very quickly see the connection to something in real life. The same is here, where you have kind of bland theory, kind of bland controller, but if you actually have something to play with, then you can very quickly make the connection again to some type of real-life application. One last example, because I can see your eyes glazing over as you look at this equation. This is a swing-up controller for an inverted pendulum, which isn't a lot of fun unless you actually have an inverted pendulum to play with. So when students are able to master this concept and actually get this inverted pendulum to stay up in the air, it really excites them. You can kind of see them mesmerized as they look at this thing. And sometimes if it's really steady, they almost will think that the thing is standing up on its own without any type of controller. And of course there are a lot of different applications of that type of inverted pendulum problem. Now, I hear a lot that hands-on learning is really great, and we've heard quite a number of speakers today talk about hands-on learning. It's fantastic. A lot of people really think it's the way to go. But when I meet with many of your colleagues, I hear a couple of common problems. There's no money, especially when it comes to equipment. The other thing too is that there's even less money for teaching equipment. Maybe there's for research equipment, but when it comes to teaching equipment, it's just not there. And even if they have the money budget, there's usually no space. So where are they going to put this different equipment that they get? And the last step is that even if they have everything, there's very limited resources when it comes to actually putting together a lab course. They need to develop new curriculum. They need to, and the faculty is usually overwhelmed already with taking on more responsibilities. So fortunately, there are a few examples of how schools have addressed this. And one of the concepts that we took from Dr. Mark Spong, who's the Dean of Engineering at the University of Texas in Dallas, is out of the Integrated Learning Center. And it basically goes like this. Within engineering schools, you have multiple departments, all spending budget independently to purchase equipment that has, for teaching similar courses, has similar uses. Instead of them purchasing equipment independently, they can pool their resources and end up freeing a lot of budget. They can end up sharing equipment, sharing lab space, even sharing lab staff. And the result of this is that they can invest in other areas, either getting new faculty or getting more research equipment or even meeting budget sometimes. So this isn't easy. And it usually requires a lot of grassroots support within multiple departments, different instructors working together. But when it does happen, the results are incredible. And an example of this is at the University of Colorado in Boulder. I visited there back in November, and they have a center called the Integrated Teaching and Learning Lab. And when you walk into this building, it's absolutely amazing. It's bright, it's airy, there are different experiments scattered throughout the building. And then you have these workstations where you really get the feeling of being a kid back in a science center. And how it works is that these different workstations, they can basically roll up different carts to teach different topics, but they can all use the same basic workstations. The other really neat thing is that different instructors can log on to a web portal and basically order experiments that can be set up in their labs, in their courses and during their lectures. So that's really neat. The other example is at Queen's University in Kingston, and they have a similar center where they have all of these workstations that can basically share different components. But the other neat thing for this is that even the math department is able to get in on this and share the budget. So there's two examples, but the common denominators for this type of setup are that you need some type of data acquisition, you need some type of power supply, and you need some type of software and PC in order to control the whole thing. But once you have those in place, you can actually swap out the plants for different bases to teach different concepts. So if you have an electrical engineering class coming in, you can use one base for, let's say, doing robotics controls, and then later on in the day, if you have a mechanical engineering group coming in, you can have a vibration controls experiment. So the other thing that can be shared, especially within the control side, is curriculum. So we worked this past year with a ABET program evaluator, Dr. Kangarasa, at the University of Washington, and we developed a curriculum that would make it much easier to meet ABET requirements for outcomes-based learning. So it requires those here in this room, and I guess watching, could also appreciate what goes through an ABET evaluation. So the other area of sharing, once you have this in place, is sharing equipment for use on research and graduate level. So at Concordia University, they actually use the same base for doing UAV and robotics that they use for undergraduate teaching. So they can share both research and teaching equipment in the same lab. So that's one area. Working across multiple disciplines is one area that new students are going to need to face when they finish school. The other one is working with different groups across the world. And I had the fortune a few weeks ago of meeting at the San Diego State University in their EC department, and they're going to be offering their students the ability to collaborate with students in France and work on robotics projects. And when these students finish, they're going to have the skills that are going to be used with the way the industry is trending, which is towards global work groups across multiple cultures, languages, and even time zones. So going back to the beginning, what's this renaissance in engineering education? So it's engaging the senses, all of the senses, to teach engineering principles. It's giving hands-on experiments early and throughout the education, not just towards the end of education. And it's working across different cultures, different streams of engineering, and different geographies in order to solve complex problems. This is a very exciting time to be involved in engineering education, and we have a lot to look forward to. Thank you very much.
Thank you, Lior. For more information on this topic and others, please visit the ACETA website at www.ecedha.org. Thank you.